Hello everyone, welcome back to another data analysis video. So this is the first in a series of videos where I will demonstrate how to conduct factorial ANOVA analysis. So in the previous few videos I have uh, I've demonstrated how to conduct one-way ANOVA, and in this and the preceding videos what I'll do is we'll extend that model. In today's video, I'll demonstrate a two-way independent groups factorial ANOVA. So we've got an independent groups design. The data that I'll analyze will not produce a significant interaction. I will cover that. I'll analyze some of the data in a future video and demonstrate how to interpret and report those things. But just as a quick recap, ANOVA designs, as you will remember, take categorical or group independent variables, and we use them to assess if the different groups, different categories of the independent variable differ significantly in their mean scores on some scale dependent variable that could be continuous or discrete in nature. Okay, so in previous notebooks, as I said, I've demonstrated the different types of one-way ANOVA analysis that you can conduct. One-way designs take one independent variable with multiple groups or levels, and they compare those groups on their mean scores on the dependent variable, the DV. In factorial ANOVA designs, we still have one scale dependent variable, but we can add more categorical independent variables containing observations from the same participants. And when we do that, we're going to investigate how the groups in those independent variables individually differ in terms of their scores on the DV, so-called main effects, and also if the scores on the DV are influenced by combinations of the independent variable categories, what we'd call interaction effects. Okay, so what I'll do in this video and using this notebook is demonstrate how to run a two-way independent groups factorial ANOVA design. So the DV that I'm going to use, the data set that I'm going to use, the DV is going to be a scale measure of participant scores on a questionnaire evaluating the extent to which they worry about crime. So it's measuring their fear of crime, essentially. The independent variables used in the design are going to be categorical variables of sex, which contains two groups, whether the participant was male or female, and anxiety level, which was a categorical variable, placing the participant into one of three groups, whether they were low, medium, or high in terms of their anxiety levels. I'm not sure what the origin of this data is. I think it was a data set that was connected to a stats textbook, and it's quite commonly used for kind of teaching and to demonstrate different types of analysis, as I'm going to do here today. So what I'll do is I'll work through the different stages of the analysis. Start by testing assumptions such as conducting homogeneity of variance tests using the Levene's test. Then I'll conduct the factorial ANOVA and interpret the results of both main effects and interaction between the independent variables. After which, if any of those ANOVA results are significant, I'll follow them up with post hoc tests and tests of simple effects if they're required. In this case, simple effects are not going to be required because as I've already stated, we're not going to find we have a significant interaction, but we will find we have a significant main effect from this particular data set. Okay, so let's start by importing some key software libraries that are going to be useful. I'm importing pandas, numpy, scipy, stats. I've imported seaborn and matplotlib here, but I'm unlikely to do any plotting, any visualization, and I'm importing pingouin as PG. Most of the analysis here, I'm going to use pingouin. I've demonstrated in other videos how to use some of the different methods from that software library to run analyses. It's a really good software library for this type of frequentist classical statistical analysis. So I'm going to import the data frame and save it as an object called a data frame object called crime_df for data frame. I'm going to import it using the pandas read CSV method. I've got it saved as a CSV on my laptop. And if I do that and we look at the head of the data, you can see the kind of the variables that are included. So we've got sex, which we're interested in. and they're currently numbered 1 and 2 for male and female, and anxiety level, these are also currently stored as numbers 1, 2, and 3 for low, medium, and high. Those are the two categorical independent variables we're going to look at. The dependent variable is going to be this total worry. So we've got this kind of list of scores here. This kind of I think higher values represent more fear of crime, more worry. We're not going to worry about stress and construct. These are two other variables that we're not going to use in this particular analysis. So as you can see here, the data saved in this CSV only has numbers to represent the sex category, so 1 and 2, and numbers to represent the 3 anxiety level groups. It'd be helpful to give those labels so then they're kind of to label what those numbers represent, so they're more meaningful and easier for us to interpret when we conduct the analysis. So in this case, the sex variable numbers represent 1 equals male and 2 equals female, and the anxiety level variables, that's ANGS level there, these represent 1 is low, 2 is medium, and 3 is high. So I'm going to create 2 extra columns in the data frame that map these numbers to their respective labels. So as I've done in previous videos, rather than change these, I'll leave them as they are, but I'll append two new variables to the data set that kind of map labels to these values for sex and anxiety level. Okay, but before we do that, I'm just going to run this cell here. Something interesting has happened when we've imported this particular data set using pandas. So pandas usually recognizes the correct data type for the data you're using, and you know, these are mostly numerical and some floating point decimal numbers, but it's imported them all as objects, and they're clearly not. We need the decimals to be shown as floating point data types, and we also we want our categories to be shown as objects. So what I'm going to need to do is kind of do some data wrangling on this to get it into the right sort of state that we need it in. If we look at the info as well in relation to this, so where it's imported all these things as objects, they're effectively strings, and if you kind of just looked at the info, it's showing 235 non-null entries for every variable. So it looks like we don't actually have any missing data, but that is definitely not true. So we're being tricked a little bit, and you'll be able to see how that works when I convert this in a sec. So first of all, I'm going to take quite a circuitous route to kind of tidy this data up. There's probably quicker ways to do this, and feel free to research them yourself. But all I'm going to do is I'm going to take our crime data frame object. First of all, I'm going to convert all these to numeric values, so it'll probably convert them all to floating point numbers. So I'm going to use the pandas.to_numeric method to do that. So to do that, I'm basically taking our crime data frame and I'm using crime data frame.apply, and then in parentheses I'm using pandas pd.toNumeric, and I'm asking it to coerce any errors. And if we then run this and ask for the data types, it's now showing them all as floating point numbers, so it's converted them all to decimals. This obviously isn't correct for a sex and anxiety level. We want them to be categories to the object. We'll come to that in a sec. But if I run the info again, what you can now see is we've got a number of non-null values. So we should have 235 entries, but none of these have no missing data at all. If they didn't have any missing data, they'd have 235 non-null. So this one, sex has 1 missing data value, 1 missing data point. Construct, I think, has quite a few. So there are a number of different ways we could deal with this. If we leave the missing values in, that might mess up the analysis. We need a way to kind of deal with them. And what's happened here is when we've converted it to numeric, anywhere that there was kind of an error or a missing value, they've been converted to NaN, so not a number, by this errors equals coerce parameter that we put in here. Okay, so what I'm going to do is basically just drop all the missing values from the data set. We'll still have quite a large data set to analyze. There are different views as to whether that's the right thing to do or not. You could impute those values. There are different ways to deal with them. You could replace them with random values. I'm just going to drop them. And to do that, I'm going to, so they anywhere there's a missing, any participant with a missing data point will just be dropped. So what I'm going to do is I'm going to create a new data frame object called crime data frame 2, crime underscore df2. I'm going to take our original data frame object, crime df, and just use this drop na method. If I do that and then look at our info again, what we will see is we now have 209 non-null entries for each. So all the missing values have been dropped, and we've now got this reduced data set of 209 observations or participants. Okay, so what I'll do next is I'm going to use the .map function to kind of create new variables, with categorical labels. So I've demonstrated this a few times in previous videos. I'm just creating a couple of lists. A represents these kind of integer values 1 and 2. B represents male and female. And I'm creating this new variable we're going to append to crime df2 called sex underscore cat, sex categorical, and that is going to basically be the sex variable, but we're going to map male to anywhere there's a 1 and female to anywhere there's a 2. Okay, and we're going to do the same thing. I will run that one. It's going to give us some sort of error. It doesn't like the way I've done this. Essentially, it will have worked, but it's telling me I should use the .loc method instead. It will still have worked, but that probably is a better way to do it. I'm going to do the same thing with anxiety level. Let's map him low to 1, medium to 2, high to 3. So let me run that as well. Same thing. It's telling us don't like what you've done, but if I've printed out the header of the data frame there, and you can see it has actually worked. It's put a male where there's a 1 and a female where there's a 2, medium where there's a 2, high where there's a 3, and where we have a 1 it should say low. Okay, so if I look at the info again for this data frame, now what you should see is we've still got these as numeric floating point numbers, but these two new categorical variables are objects, so they're saved as strings, which is fine for the analysis. So we've cleaned up the data, and we've got data types what allow us to do the analysis. So the first thing to do is we want to do some tests of assumptions. So you'll remember that when we're conducting ANOVA as a parametric statistical test, we need to meet certain assumptions, or we need our data to meet certain assumptions. There are a number of assumptions you need to meet. I'm just going to we're just going to check Levine's test here to see if we can assume equality of error variances for our variables. Okay, because we're doing a factorial design, we're gonna have to do that. We're gonna look at whether we have equal variances for both our independent variables on the DV. Okay, so to do that, I'm going to use to conduct Levine's in this case. In this case, using independent groups design, I'm using this pg.homoscedasticity method. So homoscedasticity is the Greek, I believe, for constant variance. Okay. And we've got a number of arguments, parameters we pass to it. If you've seen previous videos, you'll kind of recognize what these things are. Firstly, it's the data. So we want to use our crime data frame 2 with 209 participants. Our DV is the total worry variable, and that's kind of entered as a string, spelled exactly as it is on the data frame. Our grouping variable, the first one we'll look at is our sex categorical variable, and we're going to use the center as mean. Okay, we're basically going to use our measure of center for this Levine's test as the mean. I believe if you don't specify that you want to use the mean as the center, by default it uses the median, which is a slightly different test, which is the Brown-Forsyth test. Okay, so let's run that, and we'll run the one underneath. So we're doing exactly the same thing underneath, but we're using the anxiety level categories. Okay, so we've got these two nice tables for our Levine's test. We've got a Levine's value of 2.31 for our sex, and we get a p-value of 0.13, and it says equal variances. It gives us this boolean true or false. Equal variance is true. So for the sex variable, we seem to have met the assumption of homogeneity of variance. So we can assume the groups in our sex categorical variable have roughly equal variances around their group means. Okay. So the same for our anxiety level. So we've got three groups here. We've got Levine's omega 0.73, if we round that to two places, p-value of 0.48, and it's a boolean of true. So you can see from the p-values, and it gives us this nice clear decision. We're also not significant. So neither of the Levine's tests are statistically significant. This tells us we're probably safe to assume equal variances for the groups in our data set. So remember, with these tests of assumptions, such as Levine's test, such as tests of sphericity, the null hypothesis is that the variances are equal, and if you find a significant result, it's telling you they're not. Okay. In this case, with the variances being equal, it kind of makes our life a little bit simpler, because it means we can just conduct a standard ANOVA, having safely assuming we've met the assumption of homogeneity of variance. So for these two tests, we could report the results in the way shown here. So for Levine's test assessing equality of variance for the sex IV was non-significant, and we'd reported this as an F ratio. So F brackets 1207 is 2.31, P is equal to 0.13, and the Levine test on the anxiety level, the independent variable, was also non-significant. So F2, 206. So those are the between and within groups degrees of freedom. I've demonstrated how to do that previously, or mentioned how to do that previously, but for the between groups, it's the number of groups minus 1, so k minus 1, and for the within groups degrees of freedom, it's the numbers of observation minus the number of groups, so n minus k. So for sex, we had two groups, so 2 minus 1 is 1, and we had 209 participants, so we had 209 minus 2 groups, 207. Okay, hopefully that is clear. Right, so having safely conducted our Levine's test, we can now run the two-way factorial ANOVA. Okay, so we're assuming equal variances, and I'm going to use the pingouin ANOVA method. So if we'd not found equal variances, we'd need a more robust ANOVA test, such as Welch's test, but we can just use the standard ANOVA method from pingouin. So that's pg.anova, and again, I'm passing a series of arguments or parameters in the parentheses, the data that we're using, crime df2, our dv, that's total worry, and our between subjects, our independent groups factors, our categorical factors. And notice, because we've got two, I'm passing them as a list. So they're within these square brackets. I'm specifying sex, categorical, and anxiety level. And this last bit here, dot round, and then 3 in parentheses, all that means is I'm asking it to give us output rounded to 3 decimal places. Okay, so we've not got a really messy looking table essentially. But so what we're seeing here is the ANOVA output, and it gives us the variable name. Sex categorical is the main effect of the sex variable. Angs categorical is the main effect of the anxiety variable. Sex asterisk angs. So sex cat asterisk angs cat is sex times anxiety essentially. So that's the interaction term. All right. So gives us the sum of squares, the degrees of freedom, mean square, and our f values, p and our p values, and np squared is partial letter squared, so it's a measure of effect size. But what we're first interested in is our f values and our p values. And what we can see here is we've got an f value of 31.33 for sex, for the main effect of sex, and p is less than 0.001, we could say. It's not going to be exactly 0, but it's obviously to a kind of potentially infinite number of decimal places there. For anxiety, we've got an f value of 2.886 if we round that, and p is 0.06, so we'd say that's not significant if we were kind of using these arbitrary threshold for significance that's commonly used in a lot of disciplines. Likewise, for our interaction, we've got an f value of 0.49, p equals 0.61, so not significant. All right, so what we found here is there's a significant difference in fear of crime between the groups in the sex category between males and females. There isn't a significant difference in fear of crime between the anxiety level groups, low, medium, and high, and there isn't a significant interaction between sex and anxiety. So when you have a significant interaction, it's usually indicating that something different's happening on one of the independent variables depending on the level of the other independent variable. Okay, so we could report these results as I've kind of shown in the markdown text here. So the above results show that we have a significant main effect of sex, and then we've put the F degrees of freedom 1 and 203 equals 31.33, p is less than 0.001. A non-significant main effect of anxiety level F 2 and 203 degrees of freedom equals 2.86, p is equal to 0.06. And a non-significant interaction between sex and anxiety, F2 and 203, P is 0.49, F is equal to 0.49, P is equal to 0.61. Okay, so the main effects, essentially, you can think of them as what's the effect of sex if we ignore the other variable. Yeah. And in this case, so we've got a significant main effect. Usually one of them, we know we've got a difference between males and females, but we need some sort of follow-up to say, well, where does that difference lie, essentially? If we have 3 categories or more, we need to do post hoc tests with some sort of p-value adjustment to see which pairs of groups or categories significantly different from each other. In this case, for the sex variable, we only have 2 levels, male and female, so we don't need to conduct post hoc tests to assess where the significant differences are. All we need to do is obtain some descriptive statistics for each sex category individually, and then we can compare the mean scores for the 2 and see which had the highest level of total worry, okay, about crime, so total fear of crime. So that's what I'll do here is I'm basically just going to create 2 new objects, male mean and female mean. I'll use the .loc method, and we're going to basically extract all the worry scores for males from our sex category, extract all the worry scores for females using this bit of code, and then using this bit of code I'm going to use these 2 new objects, which basically are just storing the mean worry scores for males and the mean worry scores for females, and I'm just going to print them out to 2 decimal places. And there we can see, so we've got a significant difference between males and females in terms of fear of crime, and if we look at what those mean scores are, what we see is that females have higher fear of crime than males. So female mean worry score was 2.22 and the male was 1.73. Okay, so that's it. That is a factorial ANOVA with a test of assumptions. In this case, we had one significant main effect, but no significant interaction. So and our significant main effect only had 2 categories. So we didn't have to do any post hoc tests, and we didn't have to do any tests of simple effects. But we'll get onto those in forthcoming videos. Hopefully that was useful and interesting, and thank you for listening.